So, good afternoon, everyone. We are in week 5, so we will see what is discussed first, and then we'll see sample questions and solution of them. As usual, you are requested if you have some doubt during the discussion, you can ask at any time. Stop me and ask. Okay. So I'm starting presentation. So what uh, topics were been have been covered uh, in week 5? Let's see. Uh, It was all about linear functionals and transpose of linear operator, and then eigenvalue eigenvectors, and at the end diagonalization. Okay, so I'm not writing all this, but I'll go stating the results briefly, which are discussed in week 5. Okay, first result that was discussed is this: dual of dual space is isomorphic to V itself when V is a finite dimensional space over F over a field F. Okay, when it is finite dimensional, this then this result holds because professor had showed only this part, because dimension is equal, dimension of V is equal to dimension of V star. So taking dual will be dimension will be same, V star of a star, and he showed this injective morphism V star star to injective homomorphism to V. Now, because dimensions were equal, this will imply that this map is onto also. Okay, because of this finite dimension, we have isomorphism. So, second result, which was defining transpose of a linear transformation. If okay, let T from V to W be a linear transformation, then what is T transpose? T transpose is linear operator from W star to V star, which is defined means sending F to F after T. Okay, so T is given from V to W. Now, if you have something in W star, which is linear functionals on W, they're actually mapped from W to F. Now, what is T transpose? T transpose is sending this F to this map composition. Okay, T after T. So this is how it was defined. This is linear transformation. Is a linear transformation on W star, because W star and V star are vector spaces. It was shown in the class that T transpose defined like this is a linear transformation, and then it was discussed what is rank of T and T transpose. They were equal. Okay, rank of T is same as rank of T transpose. While showing this, we used two lemmas, right? Lemma one, lemma one was this that sorry, my fault. This was first lemma. Ranks of these two things were equal, and in the same time, it was shown that range of T transpose is exactly null space of annihilator of null space of. Okay. So and then matrix. What is relation between matrix representation of T and T transpose? This was I'm writing a fourth result, which was like this: P with respect to BB star is same as, okay, here I'm writing transpose. T transpose with respect to B prime star B star. Okay, where B is a basis of B, B prime is of W. So obviously B prime star will be basis of, this is dual basis. So it is basis of W star, like that. So B star is also similarly given. So relation between T and T transpose is this. They are actually transpose of each other. Matrix. Okay, then it was discussed uh, eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors. Okay, so given a linear transformation T from V to W, uh, if if you have a relation like this, T of V equal to T into V for some uh, non-zero vector V, non-zero vector V, then C is called, C is eigenvalue and V is called corresponding eigenvector. Eigenvector corresponding to C. Okay. So this is how it was defined. And then what is characteristic polynomial of T and some result about that. Characteristic polynomial was defined like this. Characteristic polynomial of T. It was defined as determinant of T minus xi. Okay. If T has matrix representation of A, which is then determinant of T minus x I is that n cross n matrix. Sorry. Okay, 1 minute. First of all, now this is definition and it ends here. Next result about linear operator. T is, let's say, V to V. Then characteristic polynomial of T is defined like this. I n. Okay. This is not isomorphism. I'm defining like same. Okay. So after this definition, it was shown that uh, similar matrices have same characteristic polynomial. Okay. I'm writing in next page. Similar matrices have same characteristic polynomial. Okay. Then it some exercise means some questions were discussed that I'm not going to discuss here. So you can look it back. Like there was this question which was interesting, that uh, if P is from V to V, defined like this. uh, V is, first of all, let me define what is V here. V is continuous set of continuous functions on R. Okay. Uh, okay. Forget about notation. R to R continuous functions. Okay. This is F from R. F continuous, or I should say integrable. Uh, okay. So defined like this: T of F is equal to, T of F is also a function. Okay. So how it is behaving? T of F evaluated at x is nothing but T 0 to x ft dt. Then this was exercise, means example in the classroom. And T has no eigenvalue, no eigenvector. T has no eigenvalue, right? So first of all, how it was shown? It was shown assuming, like, let's say lambda non-zero is a eigenvalue, then some contradiction. Then if you assume lambda equal to zero, then also you get contradiction, because using this condition, defining property of T says if lambda is non-zero, then f is of this form, x is of this form, c1 e power x by lambda. Okay. After assuming this, T of f is equal to, if T of f is same as lambda f for every x, lambda is an eigenvalue, then if lambda is non-zero, then f is of this form. But by definition, Pf at 0, lambda fx uh, f of 0 is equal to Tf 0, and Tf is 0 is 0 integral from 0 to 0 ft dt. So this is just 0. So this lambda is non-zero implies f0 is equal to 0. But f0 is equal to 0 will imply from this equation that T1 is itself is 0, because e power something is never 0. Anything is never 0. So it implies that f is completely 0. Fx is equal to 0 for every x. For every x. So this is not an eigenvector. Eigenvector is defined something to be non-zero vector which satisfies Tf is equal to lambda. So, but here we are getting completely 0. So this was contradiction in first case. Similarly, there was a second case when lambda is just 0, then Tf is completely 0. When lambda is equal to 0, then Tf x is equal to 0 for every x. This implies integral from 0 to x ft dt is equal to 0. This implies function itself is 0. Okay, ft is equal to 0 for every t in R. But then again it is contradiction, because this implies f is not an eigenvector corresponding to lambda equal to 0. Okay, this is how it was. So this is, I should say, this is good exercise using analysis and all this. Okay, anyone has doubt then can ask. Otherwise, I'm going to next result. Okay, I'm leaving this. See once more if
Can
you
you
heard out. Can you? Uh,
can you explain again these examples?
Okay. So, okay, first, let's say T has an eigenvalue. Okay. So lambda can be zero or non-zero. Only two possibility it has. So if lambda is non-zero, then uh, Pf is equal to lambda x. This implies this integral is equal to lambda into f. But if you differentiate it, okay, then you will see that first differentiate, then it will become result like this. Okay, I should see here. Okay, to differentiate both sides, then one side you have lambda df by dx, and this side you have df by dt. Sorry, df by dt. My fault. Sorry. This side you have df by dt and integral from 0 to x. So this is just fx. Okay, or okay, this is evaluated at x. This should have been become ft, I think. Okay, dx के रिस्पेक्ट में किया हमने. So here we have dx, and here we will have fx. Fx is equal to lambda df by dx. But equation like this will give solution like this. Okay. Next we see that c1 is itself 0, so f is completely 0. How c1 is 0? Because lambda is non-zero, tf is equal to lambda f. So evaluate both sides 0. Okay. This is integral from 0 to 0. This side tf ft dt. So integral will be 0, just 0. But lambda is non-zero. So f0 is equal to 0. Okay. Now put here f0 is equal to 0. This side you have 0. This side you have c1 into e power something 0, which is just 1. This implies c1 itself 0. So f is completely 0. This is contradiction because f is not an eigenvalue in this case. It should be non-zero vector if it is eigenvector. Okay. Now next is when lambda is equal to 0. When lambda is equal to 0, tf is equal to lambda f. So tf is 0 because lambda is 0 for every x. This implies integral from 0 to x ft dt is 0 for every x. Okay. So this implies ft itself is 0 for every t in R. Okay. So f is not an eigenvector. Sorry, not, because ft is itself 0. F is 0. Okay. But this is a result from analysis. I can uh, give you. I cannot give proof, but I can show you how it is. If you have, let's say, somewhere at some point, let's say your ft is positive 1, so there will be a small neighborhood where it will be positive. Your graph will be positive. Graph of f. I'm letting every here 0. Okay. So when you integrate from 0 to here up to here, you have integration 0. No, it's good. But in this range, integration from 0 to, let's say, this is, let's say, t1, and this is t2. This top point is t2 corresponding. So between this integral from t0 to t2 ft dt, by hypothesis it should be 0. But I'm saying this is not zero because 0 to t1 ft dt is 0 as function is 0, but from t1 to t2, t1 to t2 f2 dt, so this is non-zero because function is positive in this range, right? From between t1 to 2. So this is how this result is. If integrate this integration is 0 for all x, then better ft should be 0 at every point. So I think this needs no more explanation. Okay. So let's go to next result. The next things were discussed were diagonalization. Diagonalization. Matrix T from V to V. Sorry, linear transformation from V to V is uh, said to be diagonalization or diagonalizable. Said to be diagonalizable if there exists a basis consisting of eigenvectors. Okay, because if you have a basis, okay, and in that basis all elements are eigenvectors, then there is a relation like this. Okay, this is just rough work. Is P of Vi is equal to lambda I Vi, right? Then if you write matrix representation with respect to this basis, which is B, then it will become just lambda 1, lambda 2, everywhere else is 0, and so on. Diagonal matrix. Okay, so good. This was definition of diagonalization. Okay. Sorry, diagonalizable, when it is diagonalizable like this. I'm not doing diagonalization here, but this is definition. This is how it was defined. So some results about this where if you have this C from V to V, it is given like this. Let lambda be an eigenvalue, E value I am writing, E value, and V corresponding E vector. Okay. Then Fp of V, okay, is same as Fc of V, because once you have Tv is equal to Cv, what will be T square of V? First apply T here, Tv. It is just TCV. Sorry, but C is constant. It will go out. So CTV, again TV is equal to CV. So C square V. So using all these relations, T cube V is equal to C cube V. This was the first lemma in this direction. And second was that, okay, eigenspace corresponding to eigenvector, sorry, eigenvalue lambda is what? Let's say W lambda. This is eigen space corresponding to eigenvalue lambda. E value lambda. It was nothing but kernel of T minus lambda I, right? If then this diagonalization can be defined like this. V can be written as summation blue lambda lambda eigenvalues e values of V. Then V is diagonalizable. All the eigen vectors are here in corresponding to each lambda. Summation is over lambda, so corresponding to each lambda, we are taking all those eigenvectors. They will be in the basis. So okay, this was discussed that beta, this collection beta lambdas. Let's say this is your beta. So this was basis of V, basis of V, which is just summation Wi, means W lambda I, lambda even. So okay, so what is, first of all, let me point out that degree of characteristic polynomial is nothing but equal to dimension of V. Okay, so it can have only finitely many roots. So in this expression contains only finitely many W's, W lambda. Okay, because there are only finitely many uh, eigen values. Okay, what else? Okay, so if you have another result, if lambda 1 and lambda 2 are distinct eigenvalues, e values, then v1, which is, and v2 are linearly independent. Okay, where e v1 is equal to lambda 1 v1, e v2 is equal to lambda 2 v2. How is this Li? If you have distinct eigenvalues, then corresponding eigenvectors are linearly independent. Uh, F, so okay, 1 minute. Lambda 1 and lambda 2 are two distinct numbers, right? So you can get a polynomial f which vanishes on lambda 1 but not in lambda 2. Okay. For example, you can get this polynomial x minus lambda 1. This vanishes at lambda 1, not at lambda 2. Okay. So if this is your polynomial and you want to show these are Li, let me show this. Well, this is not too big. Alpha 1 v1 plus alpha 2 v2 is equal to 0. We want to show alpha 1 and alpha 2 are 0. Okay. So if this is your f and there was this lemma ft evaluated at v is equal to fc evaluated at v, right? When v is an eigenvalue corresponding to c, c was eigen, sorry, v is an eigenvector corresponding to c, which was eigenvalue. So here in this case we have lambda 1. So if you evaluate this ft, this is your ft ft at alpha 1 v1 plus alpha 2 ft for Ft alpha 2 V2, sorry, it's equal to 0 because Ft evaluating other side is 0. But this side you are getting F at C means lambda 1, alpha 1, V1. Now you see plus here it you will get F of lambda 2 from the same result. uh, Alpha 2 V2 equal to 0. Now you are having this equal to 0. So it is non-zero. It will imply alpha 2 is equal to 0. Similarly, you can get some polynomial when g is equal to, let's say, x minus lambda 2, then that similar result will show that alpha 1 is 0. So this is what was discussed in the last week. All this is all that was discussed. Okay, okay. I'm leaving this now. I'm going to see some questions. Okay, look at this. I'm drinking water. If f and g are linear functional on vector space V and C be a scalar in F, then G is equal to C into F if and only if. So actually now we don't know what C is. C might be 0 or non-zero. And what F and G are, F and G are function from V to our field F, whatever field F was. Let's say C is equal to 0, then null space of G will be, null space means kernel of G. Kernel G will be whole V contains null space of F if C is equal to 0. And it contains null space, whatever it is. So this contains, because this is the biggest subspace of V. So kernel of F. If C is non-zero, then if C is non-zero, then that goes to 0. I'm saying kernel G is equal to kernel F. Okay. If C is non-zero, then why? Let's say we show this inequality. Take something which is in kernel G, x belonging to kernel G, then G of x is equal to 0. But this implies C into fx is equal to 0. If C is non-zero, this will imply fx is equal to 0. This implies x belongs to kernel F. Okay. Now, reverse result. X belonging to kernel F. I'm saying all these lines are if and only, right? X belong to kernel F if then fx will be 0. And then C is non-zero, still we have C into fx is equal to 0 because fx is 0. But C into f is 0, then gx is 0. So yeah, x belongs to kernel of G. Okay, no need, right? In both cases, we have this the kernel G contains kernel F, right? Understood? This is true option. Now let the second be one. If you heard out, you can stop me, okay? At any time. Null space of F contains the null space of G. This is false. Okay. B fails. Why? Take something f which is non-zero. Okay. F non-zero linear functional. Then uh, kernel f is strictly smaller than V, but and C is equal to zero. Okay. Then kernel G will be G will be zero. G is zero. So implies kernel of G is equal to pura V. Okay. The null space of F cannot contain V because dimension is a subset of V itself, and kernel G is whole V. So a subset cannot contain its proper superset, I said. Okay. So this fails. Dimension V is, let's say, n. Then dimension of where F null space of F will be n minus 1, right? So V cannot be contained in kernel. Otherwise, they will be equal. One, they are subset of each other, then they will be equal. So dimension cannot be different. They will be same. Okay, so B fails. What about C? Null space of G contains range space of F. This is anyway false because null space of G. Okay, I'm writing here. C is false. Null space of G, which is kernel G, it is subset of V. And range space of F, this is subset of F. They are not subset of the same set. So how can they one contained in each other? Means there is no connection. So this is anyway false. Means this cannot be contained here. Okay. Hmm. Range space of G contains range space of F. Let's see. Take C is equal to 0, F which is non-zero linear functional. Then G is 0 because G is equal to C into F. So range of G is just 0. Okay. 0 in the field. And what about range of F? This will be whole F because F is non-zero. F is linear transformation in or linear functional. So once it has non-zero vector, it will have all the scalar multiple of that vector. So it will be completely F. Okay. So what D option is asking, range of G contains range of F. Means they are asking this region. This is false. Any doubt? Still here? No doubt, right? Okay, I'm going to next question. Let B let B be a vector space of all polynomials A be fixed in R with F be linear functional defined by this. Means integral from A to B of F B and D be differentiation operator. Then D dt of composed with F is what? So this is again This is also okay. What is F? F is from V to R, and D transpose is V to V itself, right? By definition, it was like this: dt of F like to P, this will be equal to F of dP, right? This was definition. So let's see what it is. Okay, evaluate at some point. Then dt of P is equal to F dP. Okay, and this is nothing but integral from A to B dP by dx. This is just P. Integral will come out P plus some C, and then limit from A to B. Px must is the volume, some constant. But this will be P of B plus C minus P of A plus C, and this will be equal to PB minus PA. Okay, this option is correct. Everyone understood this, right? So there was this relation. Let's say F is integration and D is differentiation. So what is the relation? Let's say I is integration or D is differentiation. Then first you integrate, then differentiate. This will be equal to identity only. If you differentiate first and then integrate, you will get okay. If not, it is non-zero. It depends on constant term. If constant terms is changed by an unknown constant c, which is we don't know. This is not equal to identity. In the last exercise we did this. Okay, but you understood this, right? Integrate inside you have dp by dx. Integration will be px, but some constant of integration will come. Let's say c1. So I suppose it is understood. So, D option is correct. All others are false. Let me see if you are listening it. Everyone understood, right?
Yes, yes.
Okay, okay. Thank you. Let's see next question. Third question is V and W are vector spaces over the field F. Is linear transformation from V to W. Which of the following statements are correct? So this was proved in the class. So if you see matrix representation, every row becomes column in transpose while taking transpose. So uh, row rank is equal to column rank. That result in third week, I think, that will show that these ranks are equal. Okay. Range of T transpose is any letter of null space of T, provided V and W are finite dimensional. So this was proved in the class. Okay. And this was similar result, means dual to this. Null space of T transpose is annihilator of range of T. Null space of T transpose is annihilator of null space of T provided this was L because of B. Annihilator of null space of T. Annihilator of null space of T. Annihilator of null space of T. Where it belongs. It is subset of first of all null space of T is subset of V. So this is subset of V star. Okay. And range of T is this is also subset of V star because T transpose is mapped from W star to V star. So this makes sense. B makes sense. But what about C? C doesn't make sense. Null space of T transpose it is subset of W star, right? And this annihilator of null space of T this is subset of V star. Linear function on V which vanishes on kernel T because kernel T is subset of V. So while talking about annihilator, kernel of the annihilator, this will be subset of V star. Okay. So let me show. Okay. If you remember, B was discussed in the classroom, but I can prove this if you wish.
Yes, yes. Can you prove this?
Okay. Okay. Thank you. Mm, okay. Let me see. Range of T transpose. I'm writing like this notation. An annihilator of null space of T is kernel T and this notation. Okay. These are my notations, and I'm going to show each they are equal if V is finite dimension, V and W. So take some X in left side, R T transpose. This implies there exists F in W star T here, such that T transpose of F is equal to X. Right now, what is this? Let's say evaluate. Now we are going to evaluate at point of kernel T. Okay, let some point Y belongs to kernel T. We want to see if X evaluated at Y is equal to 0. Question mark. If it happens, this will imply that X belongs to kernel T annihilate. X will annihilate any element of kernel T. So this is our question mark. Okay. So X evaluated at Y. We want to check if it is 0. This is equal to T transpose of F of Y. By definition of T transpose, it was F composite T evaluated at Y. But with Y is in kernel of T, so F of Ty becomes 0 and F of 0 becomes 0 because F is linear functional. 0 goes to 0. So now we see X belongs to kernel of an element and we had taken initially range of T transpose. So we got this result. R T transpose is containing kernel T annihilator. What about reverse direction? Let let X. I'm writing X again, but you understand what it means. Kernel T annihilator. Okay, and we want to see if there exists some F in W star such that T transpose F is equal to this X. Okay. So okay. So X belong to kernel T annihilator. Then X in evaluated at Y equal to 0 for every Y in kernel T. Okay, how to do this? Kernel of T annihilator. Uh, can we create F such that Ft is equal to X? What about because X is some linear functional on weights, right? So it is linear functional. This is a function on whole of V, which vanishes on kernel T. We want to lift this function. Define F from W to F such that F of small w is equal to, okay, so range of T is subspace of R, subspace of W plus, because we can factorize W into range space of T by extended basis. You can get some subspace W prime, and all together they will span whole W. Okay, so every vector in W can be factorized into this manner, unique manner, means every W has representation like W is equal to T of V plus something which is not in the range. Okay, uh, W prime. Then define f of W is equal to X of E V. Okay, it, that f is linear function. This factorization is linear, and this definition E is itself linear, X is also linear functional, so F is linear functional. F is mapped from W to F. Okay, I'm saying this F will work. So by definition, it will work. Understood? Then X is nothing but T transpose of X. So kernel T annihilator, it will be containing range of T transpose. So this part, you have doubt in this part? Sorry. क्या कर रहा हूँ मैं? Defining F, how to define F? Just define X of V, not X of V. Good. There will be a little difference here because of uh, X is annihilator of kernel T, so it will depend only on twice of V. Okay, this is well defined. Okay, I'm writing it. It is well defined. This is well defined because X is in the annihilator of kernel T. Okay, so this is done in the class. You look there. I will write here. I have got a little space. Why it is well defined, and this is linear functional. This is true because X is linear functional. But TV has got representation, right? Because TV can be something. TV is same as TV plus V prime, where V prime is in the kernel of T. So we had just to show that this map is well defined, and because X is in the annihilator of kernel of T, this both will give the same element. Even if you evaluate X at this V or X at this V, so it will only come out XV here and XV plus XV prime, but XV prime will become 0 because X is in the numerator. So this is well defined and linear functional. Okay, I'm leaving this. Okay, so next question. If A and B are n cross n matrices over F, then which of the following statements are correct? Okay, I'm thinking I'm doing unfair things. If you have doubt, you can ask me. Okay, then only I should go next question. Actually, this was discussed in the classroom. This B part. and B is nothing but dual of this, dual of B. Okay, I'm leaving this. No one is asking questions. So question for A, B are n cross n matrices over the field F, which are correct. A, B and B A have same eigenvalues. Let's say lambda is an eigenvalue of AB, then AB V is equal to lambda V multiply by B on both sides. Okay, so it will become B A B V. Here we have B lambda V, but lambda is constant. It will go out. So here we have uh, associativity. Apply associativity. Here we have BA. Here we have BV is equal to lambda B. Right. So if B is non-singular matrix, then this element, because V was V non-zero, so BV will be non-zero and lambda will be an eigenvalue of BA corresponding. What is eigenvector? BV is eigenvector. No need to say B is non-singular, or because if BV is equal to zero, okay, then this will become zero. If V is equal to zero, then A BV, this will become zero, and this is lambda V. So either lambda is zero or non-zero does not matter. Okay, this will say, this will imply V is equal to zero. So we need only non-zero lambda. Okay, when lambda is non-zero. So when lambda is non-zero and eigenvalue of AB, then this will be eigenvalue of BA, because then BB will be non-zero vector. So all non-zero eigenvalues, they are matching. I, this is correct because their characteristic polynomial are same. Characteristic polynomial. This is the other way. Characteristic polynomial are same. This result you can see in internet. I will give link in the same page. Math stacks. There is a website where it was asked, and this was because characteristic polynomial are same. This was one way, and this is other way. When lambda is non-zero, means non-zero eigenvalues of DA and AB are matching. This is the result. Okay. What about zero? Uh, this is not proved here. So AB and BA got same eigenvectors. This this might be incorrect because once you have B as eigenvector of AB, then eigenvector of BA will be BV, which might not be V. Okay. Here we have V. Here we have BV. So this is incorrect. You can get counter example by B is not identity matrix like that. This you can get counter example where this will fail. Okay. So what about C? So if I minus AB is invertible, I minus BA is not necessarily invertible. Let's see. Okay. If we want to show this is I minus BA and I minus AB, they are invertible at the same time, then this result will be false. Okay. So let's see if I'm claiming that I minus BA is also invertible. And what are A and B? They are n cross n matrices. So they are just representing linear transformation from same V to same V. Means no dimension difference. Okay. They are n dimensional spaces. Okay. So they represent uh, actually I should write F and prism. They are all represent maps from F and prism. Okay, so when it is invertible, if kernel is zero, right? Then dimensions are equal, so that will be 1 1 and onto map. And so matrix will be invertible. So I'm just going to say kernel of I minus BA is trivial, just zero and constant. Sorry, zero column. Okay. Okay. So something this will imply that I minus BA is inductive. There was a theorem like this, if you know. But because dimension of range and domain, they are same. So rank nullity theorem will say this map is onto. So I minus B will be dimension argument. Implies uh, I minus B is onto. This is okay. Let's say we are going to say kernel of I minus B is zero. I minus B apply some x and we are getting zero. Let's say x is in the kernel and we are going to say so that x is zero. So kernel will be trivial. Apply a from left side. It will become a minus ABA x is equal to 0. We want to use this result. I minus AB is invertible. Okay. What is written here? Take common from right side. Then it is written I minus AB. Here you have A applied to x is equal to 0. Right? This implies this is next step. Multiplying A left from left. Okay. So this is invertible matrix. And in this equation, you multiply by inverse both sides, you will get Ax is equal to 0. Right? Now, if you have Ax is equal to 0, then from the first line, okay, this, let's say this is your star, okay, this implies I minus BA, right, for X is equal to 0. This is given. Hypothesis may we have taken it. But this is implying uh, X is equal to BAX. But AX is equal to 0. We just got because of invertibility of this I minus AB. So this is what? B into 0. But B into 0 is nothing but 0. So X is 0. So anything in the kernel of I minus BA is 0. So kernel of I minus BA trivial. This implies I minus BA is injective and surjective also. So invertible. Okay. Let me see. So, so because here it was not necessarily invertible, this failed. I assumed this and proved this is also invertible. So this is tricky a little bit. You want to see it once more. Understood. I can go to next question. Okay. There is B part. I will say. You understood C, right? Suppose you understood C. So what B part says, if AB is invertible, then columns of A cannot be in the solution space of Bx. Let's say columns of A is written like A is nothing but column first, column second, like this, column n, no comma. Okay, this is your A. Then if they are in the solution space of B, what will happen? See, Bx is equal to 0 is given. AB is invertible. AB is invertible. So multiply by A both sides. Okay, then AB x is equal to 0. But this will imply x is 0. So the only solution is x is equal to 0, right? Okay, columns of A. Okay, AB is invertible. Then when claim is B, BA are both invertible, right? How? B represents this map from V to V, Fn to Fn. A represents this map Fn to Fn. This composition, okay, this composition is 1 1 and 2 map. So because this is Fn, this is Fn, this is Fn. So this map is anyway 1 1 and 2 होगा पूरा. B is also 1 1 and 2, A is also 1 1 and 2. So columns of A are non-zero. If A is C1, Cn, then Ci's are non-zero because A is invertible. So X cannot be Ci. X cannot be Ci. Okay. So I'm not showing that AB is invertible, then A is invertible, B is also invertible. This will fail in some particular cases when order of them is like this: M cross N, B is this N cross M, and now it is invertible. Then I'm not saying A is invertible and B is invertible. Okay, I'm saying when M is equal to N. Then if multiplication or composition is invertible and dimension is same, then I'm saying they are invertible. Okay, so X cannot be any of Ci because X is 0 and Ci's are non-zero. So what D says, columns A, columns of A cannot be. This is correct. They cannot satisfy this equation. Ci, okay, because N B are N cross N matrices. Here M is equal to N, so B is invertible. Invertible. This will imply B is invertible, and so X is equal to 0. This also implies A is invertible, so Ci's are non-zero. This will imply Ci's are columns of A. Okay, I think you understood this part also. Okay, what I'm doing here is using rank nullity theorem. Okay, A is injective, then first B is injective. Why B is surjective? Because of dimension argument, rank nullity theorem, like this. So B is isomorphism in that. Okay, so let's see next question. Is linear operator on R5? This video will be available in YouTube. So at any time, uh, if you have a question, what I had said, you can comment there. Okay, so because you are not uh, asking here, I suppose you can ask again if you see. Is linear operator on R5 means he is from R5 to R5 map, linear map. Okay, so even by this, which of the following statement is correct? So what is stand? If you take B, sorry, take B is equal to E1, E2, E3, E4, E5 standard basis of R5. Then uh, what is matrix representation of B with respect to this? First t e1 is equal to e1. First column will be 1 comma 0 0. T e2 is equal to 0. This whole column will become 0. T e3 is equal to e3. Right. So here you have 1 1. Third coordinate means e3. Quotient of e3 is 1. Everything else is 0. So similarly, it is 0 because e4 is not doing anything. Last is going e5 going to e5. So this is okay. Note that e1 is what? E1 is this vector 1 comma 0 0. Similarly, e4 is what? 0 0 0 1 0. Okay, this is how it's done. So this is matrix representation of T. Note that this is in the diagonal. Non-zero entries which happens they are in the diagonal. Everything else is 0. So T is diagonal as well. This is false. Now what will be the characteristic polynomial of T? This will be determinant of, let's say this is your matrix A, determinant of A minus lambda I. This is your characteristic polynomial. Okay. And what it is? X minus 1. This is 3 times. And X is square 2 times. Okay. So it was 1 minus X 3 times. But I'm writing X minus 1 3 times. While writing characteristic equation, okay, I'm writing here, let's say 1 minus X. No need to change. But when you solve characteristic polynomial, it means characteristic equation. Uh, actually, you can this this equation means determinant of a minus lambda I is equal to 0. This equation and determinant of lambda I minus a, they are same. They will give same polynomial. Means they will give same equation. That is why I was thinking like so. This is one. So okay, this is correct option. This is false. It was assumed that these two represent same characteristic polynomial. Okay, there is definition mistake, but first option is correct. Okay, Uh, we are getting characteristic polynomial minus of x minus 1 cube x square by this definition. But while writing characteristic equation, equal means equal to 0 will come. Minus will go away. So your simpler form of characteristic equation will become this. Okay. Okay. So I suppose you understood this. There was this definition problem, but this is correct because while writing characteristic equation, one is being root 3 times and 0 is root 2 times. I suppose you understood this. So I'm going to next question. Is linear operator represented by this matrix? Characteristic values of t are. We have half an hour, 5 questions. So I have done some calculations already. I looked into them. That will be easy for us. Okay, so we want to calculate characteristic values of t. So first write characteristic polynomial. What is that? A minus x I. Some people write lambda. Something. It's just a variable, so I'm writing x. So this is determinant of minus 9 minus x, 4, 4 minus 8, 3 minus x, 4 minus 16, 8, 7 minus x. This. So what it will be? Minus 9 minus x. And this will become 3 minus x, 7 minus x, minus 32. 8 into 4 is 32. Okay. Minus 4 according. Leaving first row and second column. So this will become minus 8, 7 minus x plus 64. 16 into 4. Okay. So third term is plus 4 into 8 into 8 is minus 64. Minus 16 become plus 16 into 3 minus 6. Okay. So let write here minus 9 minus x, and in the bracket it becomes multiply them. So it becomes 21 plus x square minus 10x minus 32 as it is minus 4. This becomes minus 56 plus 8x, and it is 64 plus 4 into what is inside minus 64 plus 48 minus 16x, right? Okay, next line. Multiply this. Okay. So what is here inside? Take this together. So this is written minus 11, and with 9 it will become plus 99. Okay. Minus 9 multiplied to x square will become minus 9x square. Minus 9 multiplied to minus 10x, this will become plus 90x. Okay. Now minus x multiplied to x square will become minus x cubed. Minus x multiplied to 10x, it will become plus 10x square. Minus x multiplied to this 11 minus 11 will become plus 11x. Now what second term is 4 into this. What is inside? 64 minus 56 is just 8. 8 plus 8x. So this is multiplying by minus 4 is just 32. 32 minus 32x. Third term from here, what is coming out? 16 into 4 is 64. 16 into 3 is 48. So this difference is 16. So minus 16 into 4 is minus 64. And so leave plus it. Minus 16x into 4 is equal to minus 64x. So calculating all this, this becomes minus x cube plus x square plus 5x plus 3. Let's see if it is true. Minus x cube is here. 10x square minus 9x square. This x square is here. 90x 90 11 101 and 32 64. 64 and 32x, they become 96x. So minus 96. 101x minus 96x, that will become 5x. So constant 99. Okay, again 32 and 64. This is 96, and we have 99 here. 99 minus 96 will become 3. So this is correct. So your characteristic polynomial is this. Oh, okay. So let's verify this. Okay, I am writing here. It is minus of x plus 1 whole square x minus 3. Okay, I have checked it. You also check it if you will. Note that minus 1 verifies this equation. So x plus 1 will be 1 factor. 3 verifies this equation, so x minus 3 will be 1 factor. So another factor that will be left after cosenting, it will be x plus 1 only. So this is correct. Okay, we have less time, so let's see. Next question. Okay, so there was nothing to do a special thing. Just calculate characteristic polynomial and then get the roots. They will be characteristic values or eigenvalues. Okay, so next question is similar. You have a matrix and you want to see if it is diagonalizable or tri- trigonal, means triangular matrix. So we have to calculate first characteristic polynomial. That will be the first step. So here it will be determinant a minus xi. This will be determinant of 6 minus x minus 3 minus 2, 4 minus 1 minus 2, 10 minus x here minus 5 minus 3 minus x. So okay. So what is determinant? Let's calculate it. 6 minus x. Here it will become 1 plus x, 3 plus x. Taking minus common out and then cancel common. Minus 5 into 2. Minus 5 become plus 12 minus 7. This is minus 10. It's cancelled around first row. So it will become plus 3 into 4 into 3 minus x. 4 into minus 3 minus x. 10 into 2. But this will become plus because of this minus 2. Plus 20. Third minus 2. It will become 4 minus 5 means minus 20. And 10, 1 minus x. Minus minus become plus. Then it will become 10 plus 10x. Hmm. Okay, so what it will become? X 6 minus x inside 3 plus x square plus 4x minus 10 plus into minus 12 minus 4x plus 20 minus 2 minus 20 plus 10 will become minus 10 plus 10x. Next step, multiply all of them and get 6 minus x inside it x square plus 4x minus 7 3 3, this was 3 3 minus, and here just multiply them. What is 3 into 8 minus 12 24 minus 3 into 4 is 12x, and in this you get 2 into 10 20 minus 20x. Okay, multiply this first equation, then this becomes 6x square plus 24x minus 52 minus x cube minus 4x square plus 7x plus 24 minus 12x plus 20 minus 20x. Okay. Now, at the end, it is becoming x cube plus 2x square minus x plus 2. Okay. This is your equation, characteristic equation, and this is having factorization minus x minus 2 x square plus 1. Okay. So it does not have all the eigenvalue inside R. It has complex eigenvalues. Okay. So uh, it is diagonalizable over R. This is false. Similar to diagonal matrix means diagonalizable by definition. A is similar over C to a diagonal matrix. Yes, A is similar to what? To I minus I. All three different eigenvalues. So this is correct. So uh, next, A is not similar over R to a triangular matrix. Okay, if it was triangular, uh, okay, I'm leaving this question mark, but this is obviously not correct because once it is diagonalizable, they are actually triangularizable. This is also triangular matrix, right? Triangular as well as diagonal is both. Triangular means just lower, upper triangular means just lower triangle is zero. That's all. So this is uh, triangular also. So D is incorrect. They are saying that it is not triangularizable. So overall, how to see if triangular, it is representing triangular matrix. I'm leaving this as of now. Let's see if next time I can do this. This is exercise for you. Okay, I don't know how to do this. Okay, 1 minute. If it is triangular matrix, if A is some triangular matrix, upper triangular matrix, C1, C2, C3, and here some non-zero entries, but these are zero, then I'm saying these real numbers. This is over R. I'm writing over R. C1, C2, C3 are eigenvalues of A. But there exist no three real numbers. I'm just saying कि, C1 is equal to, let's say we are getting 2, right? But C2, C3, they are I and minus I. We know eigenvalues, right? So what is if A is having this triangular form? If इसके लिए लिखना है part C. If A is of this form, what is characteristic polynomial of A from here? Yes, A is equal to. This is nothing but product of X minus Ci's. But we do not have factorization of this characteristic polynomial of A into this form where all Ci's are real numbers, right? So this is also incorrect. No need to. I'm not leaving this. So this is particularly part for part C. You understood no such C1 and C2. and C3 exists in real numbers such that characteristic polynomial factors into x minus ci. Okay, so seventh question, I suppose you understood. See, this is all due to this factor x square plus 1. What are these factors? X square plus 1. Okay, so let's see eighth question. We have 15 minutes left. Three more questions. P be a linear operator on R4 given by this matrix with respect to extended basis. Then which of the following statement is our correct? Okay. Question is asking about diagonalizer. Is diagonalizer or not? So what is characteristic polynomial of P? Here, this is lower triangular matrix or the diagonal entries are 0. So this is nothing but just product of x minus 0 four times. Mm, this four times. And then this product is four times. I'm writing here like this, but you understand. So this is nothing but x power 4. Calculate the determinant and all determinant of a minus xi. It will become x power 4. So the only eigenvalue is 0. X is 0. Only eigenvalue. Okay. So once you have eigenvalue 0, so what will corresponding to eigenvalue 0, you want to get you will get only eigenspace, one eigenspace, W0, right? Is only eigenspace W0 is what? P minus P means A here. P minus Xi. Only eigenspace. When T is diagonalizable, then this was result V whole space V can be written as sum of W lambdas, right? But here we have only one thing, so this is nothing but W0, and this is just kernel of T minus Xi means I'm writing A minus Xi, but X is 0, so this is nothing but kernel of A because Xi is 0 then. So when kernel of A is whole V, then only T or A is said to be diagonal. The I'm writing A is diagonal. This will happen. But this will happen. Whole space can be kernel of some map if and only if A0 matrix, right? Right? Here we have four transformers. Four transformers. When kernel of A is whole space V, what A should be? A should be 0. Okay. So all ABC are equal to 0. A itself is 0 matrix. So this is only option correct. These are incorrect. Okay. So I suppose I understood. Next, I'm going to next question. Question 9. A is 21 cross 21. We have 10 more minutes. Uh, A is 21 cross 21 diagonal matrix. Okay. Something like this. C1, C1, two times. Then C2, C2, three times. C2, C2, C2. Then C3, three times, and so on. I'm not writing it. Everywhere else is 0. C1, C2 are distinct. then C5 are all distinct. V be the collection of 21 cross 21 matrices. This is also 21 cross 21 matrices B on C, such that they commute with it. This is given particularly, this is A, so we want to calculate all B in M21 or C, such that AB is equal to BA. Okay? And it will come out that this is a subspace of M21. This is subspace of M20. And they are asking the dimension of this W, which is subspace. Okay. So how to do this? For motivation, I'm going to do a simple example, and then you will understand what is happening. Okay. So simply take this matrix 1 and 2. They are distinct. Okay. 2 cross 2 simply, and random element of W x1, x2, x3, x4. We want to see what is relation between these coordinates. Okay. Then we will understand number of free variable. They will be the dimension of W. This is how we do. Okay. So multiplying it from left side, we get 1 means x1, x2, and in the second row, x3, x4. And from right side, if you multiply x1, x2, x3, 4, 1, 0, 0, 2, you will get first column multiplied by 1, x1, x3, here, 2x2, 2x3, sorry, x4. And the condition that this element belongs to W, saying that these two are equal. So uh, x1, x2, x3, x4 belongs to W implies that uh, x should be equal. Okay, what is wrong here? Second row is multiplied by 2. So this will imply that 2x2 is equal to x2 and 2x3 is equal to x3. These coordinates. Okay, everything else is remaining same, right? Diagonal block is block. Nothing is changed. If you multiply from left or right, it is becoming 2x2, 2x4. Here also it becomes 2x4. So nothing is changed. But these two places, these two will imply that x2 is equal to 0 and x3 is equal to 0. So if you write 21 cross 21 matrix, then uh, and this condition, they will say that first block, which is x1, x2, 2 cross 2 block, x3, x4. This block is same if you multiply from left or right, but other entries in this block are 0. Next 3 cross 3 block you will get where A, B, C, D, E, F, G, H, I, K, where if you multiply from left this kind of matrix A, right, this block is remaining same, but everything else is 0. I'm leaving this, you understood. So what three variable will be left? They will be left in these blocks, this kind of blocks, right? You can do calculation for three cross three and then you will understand it better. So you are getting three variables, 2 cross 2 means 4 from here, 9 from here, plus 3 cross 3. plus 4 cross 4 plus 5 cross 5 plus 6, 7 cross 7. Okay, these three variables you are getting being inside W. Okay, all others are getting 0 because of this condition AB equal to BA. So this is 4 plus 9 plus 16 plus 25 plus 49. 9, 14, 29, 20, 44, 54, 54 plus 49,
103.
103. That's 103. Only option is everything else is 8. Okay, this is how you calculate for dimension of any subspace. Apply
What
all
about
the
36, sir?
what?
36, 6 square.
No 6 square is here. Means after 3, 5 block you have 7 block because 2 plus 3 plus 4 plus 5
Ah, okay,
plus
okay.
7.
Okay, sir.
This is 21. Okay, so this is main idea. How to calculate dimension of some subspace? Apply all the condition you have being inside subspace, and then check number of free variables. Okay, so this was the idea, and you get it 103 in this case. So this is last question, and we have 3 more minutes, 4 more minutes. So I suppose I can do this. Is a function from V defined like this, V to V. Okay, T is from V to V. Getting a f, which is continuous function from this is not given, R to R. This is also continuous function. Okay, so it's linear functional. No, no, it is not from map. It is not map from T to V to F. F is constant. So this is not linear functional, and this is linear operator because getting a constant function, sorry, continuous function from R to R. It was not written here, but it is supposed to be. F is from R to R, uh, continuous. So he is a linear operator. Good. He is a linear operator and has eigenvalue. Okay, this is what I discussed before the class. Means during the discussion of this was also discussed inside the classroom. So this is failing. It has no eigenvalue, right? This is how it is defined. I had shown this part. It has no eigenvalue. Okay, so T is a linear transformation. Yes, it does not have any eigenvalue. This is correct. Already discussed. Okay.
Sir,
Yes.
few words about difference between linear functional and linear operator.
Okay. What is linear transformation? V to W, a map F is linear transformation if f of C V plus V prime is equal to C into FV plus f of V prime, or every C in F field and V prime in V. So linear operator, F is linear operator linear operator if V is equal to W. Okay? It is linear transformation. But it is linear functional functional if W is equal to field F, this field. Okay, they are all linear transformation. This is also linear transformation. But when we say linear operator, we are assuming that W is nothing but V, and we say linear functional if the codomain, that is field, associated field, which is V, W, R vector space over same field. This is the main difference. This is also done inside the classroom. This is what you are asking, right? Or I misunderstood?
No, yes, sir. It's correct. Thank
Okay,
you.
okay. Thank you. Class over today. If you
Sir,
have
what
more
about
doubt,
the link? You told something about the link you will send.
what?
Some
Hmm.
link?
Okay, okay. I will send that link into this PDF. You can copy from it and take it from internet.
You will
Okay.
upload this video.
I will upload this video in YouTube. You can see it once more if you wish.
Okay.
Okay. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.